So in 5.2, we're going to continue to find areas. We want to find areas, and you can use that limit, infinite limit of Riemann sums in some situations. We don't use it very often because it really, we're limited in what we can use. So we can use it for. All right. But let's find some other areas that you'll see. Now, here's an interesting problem. Let's evaluate the integral from 3 to 6 of square root of 9 minus x minus 3 squared dx. Okay, so this looks like it could be really, really complicated. What we're going to do is we're going to graph this function. We always want to rely on the graphs before we get started, so that we can see exactly what it is we need to do. So if we graph this, we notice it's a semicircle, right? And so we do not want to try to cover this with rectangles and set up a Riemann sum and evaluate a limit as x goes to infinity, because this area that we're identifying, which is always between the function and the graph, right? This area is simply a semicircle. So what you're going to see in this section are graphs that create familiar geometric shapes, so either rectangles or triangles or circles. And so to find the area, do not do, the Riemann sum approach. You're simply going to come in here and you can say, okay, the area of a semicircle is pi r squared divided by 2, right? The area of a circle is pi r squared. So the radius here, it looks like our radius is 3. So in this case, it's going to be a 9 pi over 2. That's our area, right? 3 squared is 9. And so we can find the areas if they're a geometric shape using this approach. Okay? Now, let's try another one real quick. All right, so let's evaluate this integral. So if we look at it, we're dealing with the function y equals 2x, which we know is a line with slope 2, and we're interested in it running from the area from minus 3 to 3. And so there it is, right? And so if I pencil this in, there we go. We're finding that area right there. Now, here's the thing you have to understand. In this approach, when I evaluate this limit, let's do it first, and then I'll talk about it. We've got two triangles, right? So let's do this triangle first. So the area here, of course, since it's a triangle, so the area of a triangle is 1/2 base times height. So in our case, the base is 3, so 1/2 base is 3. The height is 2x or 6. So it looks to me like the whole area is 6 for that particular triangle. Similarly, this area, if I calculate it just as an area, is going to be 6, 1/2 base times height. But here's the deal. The integral actually sees this as a negative. It calculates it as a negative area. Part of the reason is because when if we were covering this as rectangles, we would be plugging in different x values to find the height of the rectangle. And that height is going to be a negative value. So when you do the negative times the negative value times the width, the delta x, you're going to get a negative. So the Riemann sum actually sees any area below the x-axis as a negative area. So that's why we have the -6. So here's the deal. If I'm evaluating the limit, or this integral right here, I have to honor that, and I'll treat the areas above the x-axis as positive. I'll treat the areas below the x-axis as negative, and I have to do it like that. And so when I add those, I get 0. So the integral, or the limit of the Riemann sum, treats those as negatives and keeps them as negatives. So that's why we get the answer of 0. Okay, so if we evaluate that integral, the answer is 0. Okay, now there are different kinds of questions, though. We might see a question that says, find the net area. Okay, and the net area is what we did here, right? So that means, in other words, take your positive areas and add to them your negative areas, and that will give you the net, what do they call it? The net signed area, okay? So that's the net. I'll squeeze in this. Sometimes it's called the net area or the net signed area. So you have to keep the negatives negative and the positives positive and just add them together. And sometimes you'll get an answer that doesn't make sense, right? I mean, as an area, but mathematically the net signed area is 0. However, sometimes they'll ask you a question like this: find the total area. In other words, what they're asking you to do is imagine, again, look at our picture here. Imagine, this is, I don't know, this is the shape of your garden, these two triangles. And so what's the area of your garden? Well, we're not interested in treating this as a 6 and a -6 and getting a sum of 0 and saying, oh, our area is 0, so we need, 0 amount of fertilizer, for instance, or grass or whatever, right? When we ask about the total area, what they're doing is they're asking us to say, okay, treat these as positive. So that's positive. And then they actually say this right here. You're gonna take this negative area and take its absolute value. All right. So you're going to convert any negative areas to positive areas. So plus, and then you'll add them together. Plus the absolute value of -6, so that's 12. So the area of your garden which is these two triangles, is 12. And that's right. So if we do need to find the total area, they'll say something like that, in which case you want to treat negative areas as positive areas and just add them together. But if we're evaluating the limit, or the integral, using this integral sign, it sees them and keeps them as negative areas, and so you add those together, you get that. You're finding the net signed area. So two different things, but we're using a slightly different interpretation. So be aware, if it's got the integral sign, or if it says find the net area, you got to keep the negative areas negative. If you want to find the total area, then the negative areas you'll make positive and just add them all together.